Welcome back, students, to Unit 8, Chemistry, Thermochemistry, and Gases. Today, we will be talking about thermodynamics and thermochemistry. Thermodynamics is summed up by 3 laws, including a 4th one that's just understood. So the 0th law, the most simple law of thermodynamics, is that if you have 3 objects and one of them is at a certain temperature, let's say 10 degrees, and the other object is also at 10 degrees and the third object is at 10 degrees, then object 1 and 3 are the same. And that temperature is proportional to the amount of energy a substance contains. So the more molecules move, the higher the temperature. So as temperature increases, the amount of energy in a substance increases. Now that energy can neither be created nor destroyed. So if we start a reaction with 298 joules, we have to end with 298 joules. If our reactants have a certain amount of energy, our products will have that amount of energy. Speaking of products and reactants, when we put something into reaction, we see it as a positive. It is added. So reactants will have a positive energy associated with them, whereas energy that comes out of reaction is seen as being lost. So products will have a negative energy associated with them. In chemistry, in thermodynamics, when we talk about energy, positive and negative is a direction. Positive is associated with reactants and negative is associated with products. The second law of thermodynamics is that everything moves towards chaos. Everything becomes more chaotic over time. Chaos is another word for chaos is entropy. We denote entropy with the variable S. And the amount of chaos in something, the amount of movement in it, is such a massive number that we usually focus on how entropy changes, whether something becomes more chaotic, whether entropy increases if it is positive, or if something becomes more ordered, if the movement decreases, it becomes negative. The universe favors entropy. That's the second law of thermodynamics. And finally, the third law of thermodynamics is that if you are at absolute zero, a negative 273 degrees Celsius, then all movement stops and entropy reaches 0. This is known as a perfect crystal solid. In AP Chemistry, we will talk about the third law of thermodynamics a little bit more. For this course, really all you need to know about the third law of thermodynamics is that absolute zero, or 0 Kelvin, is a negative 273 degrees Celsius. So speaking of entropy, the second law of thermodynamics, entropy is a measurement of chaos or randomness in a system. The more movement of the particles within a substance have, the greater chaos there is. So solids would have the most order and very low entropy. However, if you heat up a solid, if you overcome some of its intermolecular forces or weaken some of its intermolecular forces and form a liquid, liquids have a middle amount of entropy or chaos. If I have a liquid and I dissolve something in it, there are now more particles in solution. Those particles will run into others, and this will increase the chaos. So aqueous systems are a little bit more disordered, have a little bit more entropy than liquids, which have a little bit more than solids. Gases would have the greatest amount of energy, as gases are in constant motion, and we will speak a lot about gases at the end of this unit. So if I have solid ice chips and liquid water, which one has more entropy, more movement? Even though they are ice chips, are still in a crystalline lattice, so they have significantly less entropy than the liquids. Along those lines, for the SOL, for this course, you do not have to be able to calculate entropy. That is an AP level question. But what you will need to be able to do is tell me which of 2 substances or which of 4 substances has the greatest change in entropy. So if we have something that goes from being a solid to a gas, that would be an increase in entropy. Or if we have two gases that combine to form a single solid, that is a large decrease in entropy. Or if two gases combine to form a single gas, we start with two gases, we end with less, that is also a decrease in entropy. So towards that end, you should be able to answer the first two note quiz questions. Pause the video and answer note quiz questions 1 and 2. For these, you should look at the states of matter and how many gases there are on each side. So for example, in A, we have two gases that combine to form two gases. This has almost a neutral, or this has very little change in entropy for this reaction. However, if we have 1.5 gases that become a single gas, this would have a negative entropy. So pause the video and answer note quiz questions 1 and 2. Thermodynamics deals with energy, and in 8th grade you learned about two types of energy: potential energy and kinetic energy. Kinetic energy is energy of motion, so as things move. Now, in chemistry, we keep track of the motion of stuff as a temperature, specifically its temperature in Kelvin. So when we talk about kinetic energy in this class, we'll often talk about the energy of motion. In 8th grade, you learned about potential energy, which was based off location. Potential energy, or energy of location, energy based on location does not really apply in chemistry because the top of a beaker and the bottom of a beaker are effectively the same. And so we don't talk about potential energy in chemistry in terms of location. We talk about it in terms of the energy stored in bonds, or its enthalpy. Enthalpy, or sometimes referred to as its heat, deals with how much energy is stored within that substance. If we have a reaction and energy goes into that reaction, it'll be felt as cold because it will absorb that entropy. Entropy is denoted as the variable H, so energy that goes into reaction would have a positive enthalpy. This is known as an endothermic reaction. Energy goes into that reaction. Endothermic, in, they kind of go together. So if you ever see a positive delta H, that means that heat is part of the reactants of that reaction. A reaction that gives off energy is said to be exothermic. Energy exits the system. And so enthalpy is denoted as a negative value, as energy is part of the products. The heat given off from a reaction, is put in the product side of the reaction and would be a negative enthalpy. Whereas energy that went into a reaction, an endothermic reaction, would have a positive enthalpy. Again, positive denotes reactants and negative denotes products. The energy stored in things has a couple different units. In this course, we will focus primarily on the joule, as it is the amount of energy needed to exert 1 Newton on an object. This is the SI unit, the one that's most commonly used. We'll use joules or kilojoules, which would be 1,000 joules, most often in this course. However, in the United States, we also have the calorie. A calorie is the amount of energy it takes to heat 1 gram of water 1 degree Celsius. So you've seen calories before on your food labels. Small thing to note though. On your food labels, if you're eating a bag of chips and it's 110 calories, you'll see it written as 110 capital calories. Capital calories are actually kilocalories. Your bag of chips contains 110,000 calories, or enough energy to heat 110,000 grams of water 1 degree Celsius. We use capital calories for food because being that you are a 100 to 200 pound kid, it takes a lot of energy to move you. So that energy is denoted in capital calories. A calorie and a joule are related to one another by the specific heat of water, which we'll talk about in a later unit. But for right now, the conversion between calories and joules is that 1 calorie is 4.18 joules. So if I have one and need to convert to the other, I can use this conversion factor to convert from calories or joules. So if I have 1.9 calories and I want to know how many joules that is, I can put calories in the denominator so that it cancels out and convert to joules. For every 1 calorie, there are 4.18 joules. So 1.9 calories would be 7.94 joules. Or if I have joules and I want calories, I can go the other direction. For every 1 calorie, there are 4.18 joules. Joules in the denominator will cancel out. So 5.4 joules would be 1.29 calories. On the other hand, if we have kilojoules, we'll have to take an additional step here. First, we would have to figure out how many joules we have by converting from kilojoules to joules. So for every 1 kilojoule, there are 1,000 joules. This will cancel out joules, and then I can convert from joules to calories using our conversion factor. So 0.9 kilojoules would be 215 calories. If we have capital calories, it's the same process, because remember, capital calories represent 1,000 lowercase calories. And then we could convert from calories to joules. So we would get 3.76 times 10 to the 5th joules. Would be 900 capital calories. With that, we are able to do page 32 in your packet, as well as answer note quiz questions 3 and 4. Pause the video and complete page 32 and note quizzes 3 and 4. As a reaction occurs, our reactants will have some amount of enthalpy, potential energy stored in them, and our products will have another enthalpy. As that reaction occurs, you can graphically show the amount of energy our reactants have as they become products. Just because reactants collide with one another does not necessarily mean that they will form products. In order to form a product, reactants have to collide in the correct orientation. Carbon monoxide and oxygen are not going to make carbon dioxide unless they collide correctly. This is known as collision theory. Colliding correctly, just if these two were to bump into one another, does not indicate that a reaction will definitely happen. They have to have a certain amount of energy. They have to collide with each other with a certain amount of force to overcome their attraction for one another, to overcome the attraction of the carbon for the oxygen to form these new bonds. The amount of energy they need when they collide is known as their activation energy. So on this graph, as our reactants become products, the amount of energy your reactants need when they collide is this hump here. This potential energy diagram is showing a particular type of reaction in which our products have more energy than our reactants. The change in energy for the reaction, or the enthalpy of the reaction, would be if you took the potential energy of your products and subtracted the potential energy of your reactants. This change in energy of your products minus your reactants is how the energy would change as this reaction occurs. This is a positive enthalpy value, meaning this is an endothermic reaction. This reaction would feel cold as it occurs. If your reactants lose energy as they form your products, in this case, when we subtract reactants from products, we get a negative enthalpy change. The heat of reaction for this reaction is negative. So this is an exothermic reaction. Energy is given off. This reaction also shows what a catalyst does. A catalyst lowers the amount of energy your reactants need when they collide. It reduces the activation energy. Rather than require a massive amount of energy when they collide to form products, a catalyst lowers this energy, providing an alternative pathway. With that, we are done with Unit 8.2. Go ahead and answer Note Quiz questions 5, 6, and 7 through 10. For question number 10, you need to tell me whether a reaction is endothermic or exothermic, so you will need to write into the space whether it is endo or exo. I'll see you next time when we talk about changes in temperature and phase change, how it applies to enthalpy.